Hi everyone, so we're going to look at the motor effect. This is a physics topic in magnets and electromagnets. That is a higher topic on the combined and on the physics. So in this you need to know a few things. You need to know how to use an equation, and you need to know about some rules to do with your hands. So you might have been taught this, but if not, to be able to work out questions on the motor effect or understand it, you have to know about a rule called Fleming's left-hand rule. And there's a little way that you could remember it when you're in the exam, and what it's about. I'm going to talk about that with you now. So you can see the picture on the screen is a left hand held out in that particular way. So it's not particularly comfortable to hold for a long time, but it's okay for a few minutes. So you've got three fingers pointing in three very different directions. The thumb, pointing upwards at the moment, represents the force direction. So it's the force in newtons, the direction of the force. Okay, so I'll talk about what this all means in a minute. The second finger, the index finger pointing that way, represents the magnetic direction in Tesla, and the third finger, middle finger, that is represents current in amps. Okay, so these three things work together. If you have two of these things, then you can generate the other. Okay, so if you have a magnetic force, so something magnetic in a magnetic field, and you have a current, then you can generate a force. If you have, let's say, a current and a force, you can generate something magnetic. If you have magnetic and a force, you can generate a current. So the motor effect is when we have magnetic force and a current, and we generate movement through force. Okay, so this principle is applied with anything mechanical that moves, basically. Okay, so this is a question that I found. Let's see if we can apply the equation. So the equation that you're given is linking these together, but also to do with the length of a wire, because the length of a wire also affects the strength or the force. So let's have a look. We've got, for this question, we've got 2 amps, so that's the current, and we've got 50 centimetre wire, and we've been asked to calculate the force when we have a 0.4 Tesla magnetic field. So Tesla is the unit of magnetic flux density. Okay, so basically the strength of the magnet. So we've got a current, which is I, that's 2 amps. So looking at our units, that's all okay because that's our SI unit. We've got a length of wire that is 50 centimetres. So at the minute I'm going to have to look at that because centimetres isn't an SI unit. I'll come back to that. And I have a magnetic flux density of 0.4 Tesla, and Tesla is my SI unit. So at the moment, these two are okay. I need to look at this one. The first thing that I would do with this question is any converting that I need to do. So I'm going to need to convert 50 centimetres into meters, because that's SI, so that's going to be 0.5 meters. That's the first thing I'm going to do. Now it's pretty straightforward, this question, because it's already all three here. I don't have to rearrange. So the force to calculate that in newtons would just be multiplying 0.4 by 2 by 0.5. Do I need to do it in the calculator? Well, 2 times our half is 1, and then 1 times 0.4, that's just going to give us 0.4 as our answer. So force is 0.4 newtons there. So that's how you apply Fleming's left-hand rule and using the equation for the motor effect. If you found this video helpful, please subscribe to my channel. Thanks a lot.